Hello all, welcome to this webinar and thanks for attending. Today I'm going to talk about edge computing, how it is important for multiplayer gaming, and then I'm going to show a solution to deploy multiplayer game server at the edge based on different open source technologies. So in particular, we will look at how to deploy Kubernetes clusters on the edge based on K3s distribution. And then we are going to use Agones, that is an open source platform built on top of Kubernetes to deploy game servers. I will also talk about some tools by OpenNebula that allow us to deploy resources on the edge. So let me introduce myself a bit. I work at OpenNebula, that is a company based in Madrid that focuses on building open source solution for edge and cloud computing. I work remotely from Lecce, is in the south of Italy, as a cloud technical evangelist. So I engage with the community. I talk at events, webinars to showcase open source technologies that are related to cloud computing, edge computing, Kubernetes, containers, and so on. Okay, so let's move to edge computing. Now, it is not just a buzzword. It is a new real paradigm, computing paradigm, that requires some technological challenges because what we need to do is to bring the computation, data, storage closer to the location where it is needed in order to improve response times, to save bandwidth, to reduce data transfer. So edge computing plays an important role in different sectors like gaming. So this is what we are going to talk about today, but also broadcasting, streaming, Internet of Things, smart cities, and virtual desktop infrastructure. So edge computing is important for applications that require low or ultra-low latency, that require high bandwidth, fast response, real-time analytics, and these are the main benefits that we can get by using this new paradigm. If we look at multiplayer gaming, edge computing can be a game changer. Today, multiplayer online gaming represents a big percentage, of the entertainment in general. And some types of games are very popular, like first-person shooter, like Destiny 2 or Call of Duty. We have multiplayer online battle arena, like League of Legends, Dota 2, and also very popular battle royale games such as Fortnite or Apex Legends. So all those games are played worldwide by millions of players. So how they work? Usually there is a matchmaking system. So people join a queue, and then this system match players from this pool. And when there is the right number of people that can go from 10 to hundreds of people, a game is created. Now, in order to start a game server is deployed. And a game server is a dedicated server for the game between the players that are involved. So when a game starts, all players connect to these dedicated game servers, and they send information during the whole game to the game server that will process all the actions that are coming from the player. So if the player is jumping, is running, is shooting, all this information is sent to the game server that then will run the full simulation, the physics, by taking into account all the player actions. And then the server transmits data about the game state to the clients. So each client will have their own accurate version of the game state to be displayed, to be rendered by the GPU client. Okay? So edge computing is important for multiplayer online gaming because in the case of these fast-paced games, we need to lower latency as much as possible. So in order to provide a satisfying gameplay to the players. Now, we cannot use an approach based on a central data center where all game servers are deployed because this will increase latency, will decrease game response time, and also the perceived game quality. And so players will not tolerate this kind of service. Instead, by using an edge computing paradigm, we can improve the gaming experience. Why? By provisioning game servers as close as possible to the pool of users that participate to the game. And then we can drastically reduce latency. We can transmit data faster than using a large centralized data center where all game servers are deployed. Also, we have to take into account that if a game has a global deployment, so is played worldwide, there is also a need for scaling dynamically those resources in order to satisfy the demand at particular times. So in a particular time, in a time zone, you can have a peak, maybe it's the evening after the work time. And in another time zone, there is a low demand of resources because most of the people, for example, are sleeping. So we have to take into account all of this. So for multiplayer online gaming, we have to take into account these dynamically resources that must be created and deleted. And also we have to take into account latency. Now, in order to set up an edge computing solution for multiplayer game, we are going to use several technologies. So let's start from Agones. Agones is an open source platform for deploying, scaling, and orchestrating game servers for multiplayer games. And this has been built on top of Kubernetes. So Agones extends Kubernetes. So you can use standard Kubernetes tooling and APIs like kubectl to create, run, manage, and scale dedicated game server. The second technology that we are going to look is K3s. So K3s is an official now CNCF sandbox project. It's a certified Kubernetes distribution and is ideal for edge deployments because it's packaged as a single binary, less than 40 megabytes. So it has fast provisioning, comes with minimal to no operating system dependencies. It also can run on several processor architecture from Intel x86 to ARM architecture. So K3s has two components: as the server that is in charge of managing the cluster, deploying container as pods, and the K3s agent that has the function as a worker. It's in charge of running and executing pods. Okay, so now let's look at the solution that we are going to show also with the demo in a few minutes. So we are going to use a couple of tools also developed by OpenNebula. One is called OneProvision. So OneProvision is a tool that allows to dynamically grow a cloud infrastructure. So with the physical resources that runs on remote cloud providers. And so we can create resources, for example, on Equinix Metal, on AWS, on other cloud providers. And with OneProvision, we can deploy on these cloud providers a fully functional OpenNebula cluster. So with the computing, with the storage, with the networking resources. And this cluster will be managed by using OpenNebula. Computing resources will be configured by using Firecracker, that is an open source solution by Amazon Web Services. And that has been integrated in OpenNebula to create and manage secure and multi-tenant container-based services and applications. Then with another tool from OpenNebula that is called OneFlow, we are going to deploy K3s clusters on resources provisioned by OneProvision. So K3s clusters are deployed as Firecracker micro VMs. And we have to take into account that Firecracker micro VMs has a very fast startup time and a very low memory overhead with respect to traditional virtual machine. In order to deploy K3s cluster, we start from a K3s Docker image that has been built with a Docker file, and then we can define a service template that will be instantiated to deploy a K3s clusters on edge resources. So when the cluster is deployed, We can use a standard Kubernetes tool like kubectl, and we can deploy agones in the clusters, and then we can still use kubectl by deploying a game server within agones. And for example, in the demo, we are going to use Xonotic, that is an open source and a free first-person shooter, and we are going to use then the Xonotic game client to connect to the game server. Okay, so now let's see a demo. So I will show how this solution works and for multiplayer gaming at the edge. Okay, so let's start with the demo. So here we have one provision, that is the tool by OpenNebula in order to provide resources at the edge, so on remote cloud providers. So here I have defined already providers by considering AWS, the facility in London. I will show you how to create another provider. So we're going to select, in this case, packet, Equinix Meta. We are going to select the template for the Amsterdam facility. And then here we can change name, for example, Amsterdam. And then here we are going to use to configure the connection. So I'm going to the console or Equinix method. Here I defined, I created the project. If I go here, this is the project ID. So we can copy the project ID and put here. And then I defined also an API key for the demo. So I can copy this one and I put here. Okay. Now we can finish. So here the provider has been configured. When the provider has been configured, we can provision resources on that provider. So let's go and provision resources on Packet by using Firecracker as an hypervisor technology. So we select here the provider in Amsterdam. Here we can put the name, for example, MS1. And then we can configure the inputs. So the number of hosts that you would like to create, the number of public IP, for example, is set 4. Here you can select the different size for the resources for the server, and here you can choose the, for example, the operating system. So let's finish this, and now the provision will start. One provision uses Terraform to create resources, and then we'll use Ansible to configure the host. And it will going to create computing resources, so in this case 2 servers, storage, so data stores for the VM, and then the networks, the public networks with 4 public IP that we can use. Okay, now let's go to the OpenNebula Sandstone. This is the graphical user interface of OpenNebula. I will show you in the infrastructure. Now there is a cluster that has been created by one provision. I call it packet MS1. Here you can see also the host that have been is going to be provisioned. Also, I will show you in the project on Equinix. If I go on servers, here you are that the hosts are being created on Equinix Metal. So I selected the location, MS1, CentOS operating system, the T1 small configuration for the instance. Okay, so this is how to provision resources on a provider. Then let's see how we can deploy a Kubernetes clusters once we have a cluster available. So first of all, what we have to do is to create an image, a Docker image, and import in the data source in OpenNebula. Here I already imported a K3s image. I will show you how you can create an image starting from a Docker file, for example. So let's call this K3s new, and here we can define the size, and then here I have a Docker file that I can use to build an image containing K3s, no? That I will download from the GitHub repository, and here I'm going to download the version 1.17. Okay, so once you click create, what is happening here is that OpenNebula is going to build this image, is going to be contextualized with the contextualization package on OpenNebula, so we can have SSH, we can have networking, and so on. Okay, so this image will be enhanced with the contextualization package of OpenNebula. When we have the image, we can define a couple of templates for the micro VM that will be deployed on the resources with the Firecracker. So we've defined two templates, one for the server component, and here in the template you can have you can define the memory, the CPU, and we are going to associate the storage, so the image, Docker image, to this template. We can associate a network. In this case, it's automatic selection. That means that when we are going to deploy at runtime, the network belonging to the cluster will be selected. And an important thing is the context part. So here we have defined a start script. So the start script will get some information from the VM, like, for example, the public IP, and then we'll start it will start the K3s server. Also, when we execute, we launch the K3s server, a token will be generated. This token will be put as a key in the metadata server of OpenNebula that is called ONEGate, okay? Because this token will be used by the agent in order to start and to connect to the server. So we have defined also a template for the agent. So also for this, you can define memory, CPU. We associate the same image that we have defined for the server. Here also for the network is automatic. So the difference is in the context. So the start script is different. So in this case, the script is going to get, by using the ONEGate, the metadata server OpenNebula, is going to get the IP of the server, is going to get the token, and then it will start, in this case, instead of the server, is going to start the agent. Okay, once we define these two templates, we can define a template for the service, so for the cluster, where we have defined two roles, one for the server and one for the agent, and we associate the two templates that we have previously defined. Okay, so in this case, we are going to, when we are going to instantiate the service, we have cardinality for server equal to 1. That means one server will be deployed, and we will deploy two agents. In the case of the agent, I have defined, for example, a minimum VM equal to 1 and maximum VM equal to 10, with a cooldown of 2 seconds between each scaling operation. Because by using one flow, you can scale at runtime. And so, for example, if we need more agents, we can scale to more agents. Okay. So now let's instantiate the service. And here we have an attributes that we are going to pass to the template. And it will be the name of the cluster that we would like to deploy the K3s clusters. Okay, so in this case, we are going to deploy on packet, on the cluster packet MS1. And let me go to create the service. Okay, so now this service is going to create the server first, and then the agent. Okay. Here you see this in prolonged state. While this will create the K3s server, I will show you here, as you can see, the provision is finished. And here we have now you see the cluster that is in a running state. And also in the OpenNebula Sandstone graphic interface, you can see that the hosts now are on, so are available. So we can deploy the K3s clusters, the K3s cluster here. So let's look back to the. So here the service is going to now, the K3s server is going to boot and to run. And here we can see that he has a public IP that now we will use to connect to deploy Agones. Okay, so let's first download the configuration file for connecting to. So the file is still not available, so it's still starting. And copy the IP. Here you can see that the. Okay, now we started. So now we can connect to the. So we can copy the configuration file to connect to the Kubernetes cluster. So let me change the local IP with the public IP in the configuration file. And now we can export the file and we can connect. So for example, let's see which nodes. But at the moment is only the master is available, so only the server. If we look here, you see also the agent are now running. So the start script is starting also the agent. So let's check back again. Now we have also the agent that have joined the cluster. So now what we are going to do is to create, to deploy Agones on this. So we can create the namespace and then we can install Agones, okay, in the namespace. Okay, now let's check the reports. Okay, here we see that someone is already running, some are creating, and so they are okay. So once Agones has been deployed, we are going now to deploy a game server. So I've defined a file. This is a fleet, so we can deploy several game servers. So we can define, for example, the replicas, also the type of scheduling. We can decide between distributed, packet, according to if the cluster is dynamic or is static. So in this case, I will deploy this fleet, and this will be 2 game servers will be deployed on the cluster. Okay, so let me apply first this. And now we can do this. So first of all, let's check the fleet. Here we have 2 Exonotic, decided 2 current, and we don't have any game server ready. So we can check game server by using, as you see, we are using the kubectl because Agones now extend Kubernetes, so you can use the API of Kubernetes. So let's check the game server. So this will take some time because in this case we don't have the image of Exonotic on the clusters, on the Kubernetes cluster, so it's taking some time on pulling the image. We can check this by using the scribe. And then let's see here. So as you can see here, is still pulling the image. So we need to wait a bit in order to the image to be pulled. Meanwhile, just want to say that here we have deployed the clusters on Packet, right? Clearly, if we would like to deploy the clusters on another provider, for example, on AWS, so the first thing is also to provision other resources, for example, on AWS. So here, for example, let me go and also start the provisioning on AWS London, okay? So let's call it this alias London. And here we can define again the number of servers, the number of public IP. This is the NMAI for CentOS, and here we can select the instance, for the provisioning. In this case, our bare metal server from Amazon. So when I click finish here is starting the provisioning, or also this. I will show you also in this case, another cluster has been created here. Also another host, in this case I choose just one host, is going to be provisioning. And also I have here the instances, so still not running. And with Terraform is going to run to create now here an instance for in London. So let's see if okay, so now it's running. Okay, so let's go back and see if now the game server are ready. Okay, so meanwhile the image has been pulled. Now we have two game servers that are ready. And now let me show how to, so we can connect now with the client. So this is the client for Xonotic, this first-person shooter. Okay, so, and now what we can do is just join one of these game servers. Okay, so let me put here this address, and then the port. Okay, now we can join. Is loading, and now it's joining the game server. And let's see, should start. And now I am here. You can see that I am in the game, and I'm playing now the game. Okay. Here, for example, the game server has been created with some bots within. Okay, you can see that there are some bots in the game. Okay. Okay, now I can quit this. I cannot. Okay. Let's see if I can shoot this one. Maybe not. Okay. Let me quit this. So we can use the kubectl, for example, to also scale game server. So let's say we need more game server. So what we can do is using kubectl scale fleet, and then for Xonotics, let's say 4 replicas. Now, if we check the fleet, we see that we have 4 decided the current and only 2 ready, but in few seconds we will have 4 ready. Now, this is faster because we already downloaded the Xonotic image on the servers. Okay, so and then maybe we want to shut down some game servers. We can set replicas equal to 1, and now what is going to happen is that the servers are going to be shut down. So that's how it works with Fleet. Okay, so we can scale game servers. I will show also to you how to scale, for example, also the K3s cluster. So if we need more agents, we can do this by using one flow. For example, we can click on the agent, and then we can click on scale. And so let's say, for example, that instead of 2, we would like to have 3 agents. Okay. So what is going to happen now is that a new agent is going to be deployed on the resource, and this will join also the cluster. Okay. So this is for the demo. And I think that this is all. I hope that you enjoyed this webinar, and you have some fun with this deployment. And you can check also the website ONEedge.io, where you can find information about the Edge cloud architecture by OpenNebula. Okay, thanks to all for attending this webinar. Bye.